Two vertical poles, one 16 feet high and the other 24 feet high, stand 30 feet apart on a flat field. A worker wants to support both poles by running a rope from the ground to the top of each post. If the worker wants to stake both sides of rope in the ground at the same point, where should the stake be placed to use the least amount of rope? So I can do a quick sketch of what's going on in this problem. We have two vertical poles that stand 30 feet apart. So a distance of 30 feet, we have these vertical poles. One of them is 16 feet high, and the other one is 24 feet high. And this worker wants to stake them with a rope from the same point. So somewhere along this 30 feet between them, I'll choose a point and tie the rope to the top of each one of those vertical poles. So I have a better picture than my sketch there to show you that. I don't think we need it to be that big, quite that big. But it'll help us understand what this problem is about. So we want to use the least amount of rope. So this is an optimization problem. We want to use calculus techniques to solve it. So first we need to create an equation that represents the amount of rope. That amount of rope by choosing a point at different spots along this area between them. And then once we get that function, we'll use our calculus techniques to optimize or find the least amount of rope. So I want to let x be the distance between this pole on the left, which we have as 16 feet, and the point at which we stake the two ropes. And then because the total distance between the poles is 30 feet, I know that this value will be 30 minus x. So then we have a right triangle, and we can use Pythagorean Theorem to label these sides of the triangle. So Pythagorean Theorem is a squared plus b squared equals c squared. C is the hypotenuse, and a and b are the legs. So where the rope is the hypotenuse. So for this triangle here, we have legs of 16 and x. So 16 squared plus x squared is that distance squared, and 16 squared is 256, and I can square root both sides to get that hypotenuse. So we have this length of rope will be the square root of 256 plus x squared. I chose the positive because it's a distance. Then the other triangle, now we're going to write an expression that represents this side. Once again, we'll use Pythagorean Theorem, and we have legs of 30 minus x and 24. So that's 30 minus x squared plus 24 squared equals that distance squared. The 24 squared is 576. We could also multiply out this 30 minus x squared. That's 30 minus x times 30 minus x. So 30 times 30, 900, minus 30x minus 30x minus x squared, plus 576 equals d squared, our distance squared. We want to do 900 plus 576. That's 1,476 minus 60x minus x squared equals our distance squared, and we can take the square root of both sides to get 1,476 minus 60x minus x squared. So that represents the distance along this rope here. So now that we have our distances represented, we want the total distance of the rope. We'll add those two up. That'll be the square root of 256 plus x squared plus the square root of 1,476 minus 60x and I think that should be plus x squared. Let me make that correction over here. This is a negative x times a negative x, which would be a positive x squared. That's a plus x squared. So now we have an equation which represents the amount of rope no matter what point we choose. So remember, it's based on this value of x here. So we can plug in a value of x and get what the length of the rope would be for any value of x. So the next thing we want to do is get it ready, get this equation ready for us to do the calculus portion. And I'm going to rewrite these radicals as powers. So let's write this as x squared plus 256 to the 1/2 power. And I'm just rearranging the terms at the same time. That's x squared minus 60x plus 1,476 to the 1/2 power. So the process that we're going to go through as far as the calculus goes is that we're going to calculate the derivative, and then from the derivative we're going to find the critical numbers. The critical numbers are where the derivative is equal to 0 or the derivative is undefined. And then we want to test those critical numbers to see if they will provide us a minimum, a relative minimum. And we're looking for a relative minimum because we're looking for the least amount of rope. So let's calculate the derivative of our function. Our function is x squared plus 256 to the 1/2 power plus x squared minus 60x plus 1,476 to the 1/2 power. So to calculate the derivative, we're going to need to use the chain rule. So we will start with the outside function, which is the power. We bring that power down and take 1 away from the power. We leave the inside alone and multiply by the derivative of the inside, which is 2x. We're going to do the same thing with the other function, or the other term. So we bring that power down, take 1 away from the power, leave the inside alone, and chain by multiplying by the derivative of the inside. That's 2x minus 60. So we can rewrite these as 2x over 2 times x squared plus 256 to the 1/2 power plus 2x minus 60 over 2 times x squared minus 60x plus 1476 to the 1/2 power. So I'm going to start with where the derivative is undefined, because I think we can eliminate some. I can already see that we're going to get some imaginary solutions. We want to find where the derivative is undefined, and the derivative will be undefined where this denominator is equal to 0. So I'm going to set these factors equal to 0 to find where the derivative is undefined. So I have x squared plus 256 equals 0. I'm going to subtract 256 on both sides. That's x squared equals negative 256. And if I take the square root of both sides, you can see we've got the square root of a negative, which gives us complex numbers instead of real numbers. So since it is not a real number, we're not going to get a critical number from this equation. We're going to do the same thing with the other factor in the denominator. That's x squared minus 60x plus 1476. We're going to set that equal to 0. And let's try to solve this with the quadratic formula. We've got negative 60 plus or minus the square root of negative 60 squared minus 4 times a times c times 1 times 1476 over 2 times a, which is 1. So we have 60 plus or minus the square root of 3600 minus, let's see what 4 times 1476 is. That's 5,904 over 2. And once again, you can see that we're going to have a negative underneath the radical. And that negative underneath the radical means that we have no real number, and or that it's not a real number, and we have no critical numbers coming from the derivative being undefined. So then we want to consider whether the derivative can equal 0. And while I do that, I know I can cancel out these 2's. So then I want to find where the derivative is equal to 0. So I'm setting this equation of x over x squared plus 256 to the 1/2 power plus 2x minus 60. We can simplify that as well. 2 goes into 2 once, and 2 goes into 60 30 times, Let's rewrite that as x minus 30 over x squared minus 60x plus 1,476 to the 1/2 power. So to solve this equation, I would need to clear the fractions. So I'm going to get my common denominator. The common denominator is just the product of these two, and we're going to multiply by that on every term. So when we multiply 0 times, this is the left-hand side, times the common denominator, the left-hand side becomes 0. When we multiply this term x over x squared plus 250, I left off this 1/2 power here, x squared plus 256 to the 1/2 power times that common denominator, these cancel out and will leave me with x times x squared minus 60x plus 1,476 to the 1/2 power. And then we need to do the same thing to the last term. I think you guys get the idea there. So on the last term, we would have x minus 30 over x squared minus 60x plus 1,476 to the 1/2 power times that common denominator. And just the one term cancels out, so we're left with x minus 30 times x squared plus 256 to the 1/2 power. All right, so I just corrected a mistake I had right here. So in case you missed it, I drew in that 6. So from here, because we have parts of this equations that are raised to the 1/2 power, we need to get rid of those. So what I'm going to do is I'm going to move one term to the other side of the equation. And we have x, that would be negative x, times x squared minus 60x plus 1,476 to the 1/2 power equals x minus 30 to the x squared plus 256 to the 1/2 power. And then we're going to square both sides. And when we square both sides, that's going to get rid of these 1/2 powers. So I'm going to square the left-hand side. Then I'm going to square the right-hand side. And we're allowed to apply this square to the individual factors. You can only do that when you have factors inside or a quotient inside. If you have individual terms, you can't apply the square to the individual terms. So that means negative x squared is x squared, and then the 1/2 power and the squared cancel each other out. So you get x squared minus 60x plus 1,476. On the right-hand side, the same thing happens. You get x minus 30 squared the 1/2 power and the squared cancel each other out, and you get x squared plus 256. So then we want to solve this equation, and I will multiply everything out and move all the terms to the same side. That gives me on the left x to the 4th minus 60x cubed plus 1476x squared. On the right hand side, I would need to multiply this out first. That would be x squared minus 60x plus 900 and then we need to multiply out. I'm carrying this down on the left. On the right, we would have x squared times x squared is x to the 4th minus 60x cubed plus 900x squared. Then we'll multiply everything by that 256, so we have 256x squared. I need to know what 256 times 60 is. That's 15,360, and that should be negative, not positive, with an x. And then 256 times 900 is 230,400. I've got a correction on the left here. This should be an x to the 4th. And then we have our 230,400. Okay, so I'm noticing a few things that will cancel each other out. I have this x to the 4th on the left and the x to the 4th on the right that will cancel. The negative 60x cubed and the negative 60x cubed will cancel. And I have some like terms to combine. So 900 plus 256 will be 1,156x squared minus 15,360x plus 230,400. So let's subtract 1,476x squared to move everything onto the same side. Will give me negative 320x squared minus 15,360x plus 230,400. I am going to try to solve this by factoring the greatest common factor first. Okay, so all of these are divisible by 320, so I'm going to factor out a negative 320. That leaves me with x squared. 320 into 230,400 is 720. And then into 15,360, we get 48. And since I factored out a negative, that changes these signs. And we'll try to factor some more. Let's see, we want to think about factors of 720. (120 and 6). Thank you. Good catch. Okay, so only one of them is negative. So we've got a positive 60 with a negative 12. And then you can set each one of these factors equal to 0. And you get x equals 12 and x equals negative 60. The negative 60 doesn't make sense because it's a distance. So we only want to check that value of 12. So that's our critical number of 12. And you want to check to see if that critical number is a relative minimum. So I'll choose a value on each side of 12, 11, and 13 to substitute into the derivative. If it's an extrema, we'll see a change in signs, but we're really hoping for it to be a minimum. So let's use our calculator to substitute this into the derivative. So we'll type in our derivative into the y equals menu and then substitute these values in. So we have x over, we can do square root of x squared plus 256 plus, we need parentheses around the numerator, over the square root of x squared minus 60x plus 1,476. And we'll graph that. I need to change my window because it's not showing the value that I want. Our x value is 12. Our critical number is 12, so I'm going to go out to 20 here so we can see that portion of the graph. And then we'll do second trace, which gets me to the calc menu. I'm going to select number 1, which is value, and type in 11. And we get a negative, and type in 13, and we get a positive. So we've got negative and positive, that's decreasing to increasing, which creates a min. So we've got our value of x that minimizes the length of rope. So let's just go back to the original problem to make sure we answer the question. The question says, where should the stake be placed to use the least amount of rope? So the stake should be placed 12 feet from the 16-foot vertical pole. Thank you for checking out my videos. Have a great day.